We're going to talk about another concept in Chapter 1, which is resonance and arrow pushing. So resonance is a concept from Lewis structures that shows that multiple structures in a particular Lewis structure can be equivalent. So let's, for one, let's draw the Lewis structure for ozone, which is O3. So ozone, oxygen by itself has 6 electrons, and there's 3 of them, so we're going to have 18 electrons. If we arrange them in a line, which is the only possible way to arrange 3 elements or 3 atoms, we see that we've used 2 plus 2, which is 4 electrons, and then we start filling in the remaining electrons. So I can put 2, 4, 6 around here. So we have 2, 4, 6, 8, 10, 12, 14, 16, and it's clear that we're not going to make both of these have an octet, so we can put a double bond here. So this would be one structure of ozone. However, we notice that we have a single bond on one side and a double bond on the other side. But if we think about it, there's no real preference for why the double bond should be on one side and the single bond should be on the other side. So we can write what's called a resonance structure that flips those two. So we put the double bond on the other side, and we put the single bond on the side where the double bond had already been. Now we call these two structures resonance structures because functionally they're equivalent. There's no preference for one versus the other. So in fact, we can draw what's called a resonance average, where we display this as not one single bond and one double bond, but instead an average of two bonds, such that we have kind of these dotted bonds. And so each bond order would be about 1.5. So each of these would be about 1.5 bonds if we were talking about a resonance average. Now the arrow pushing for this is going to be key for demonstrating the flow of electrons in an organic reaction. So we always are going to go from electrons and to a deficit of electrons, and they're going to show a flow of electrons. Excuse me, let me erase that. We're always going to show the flow of electrons from one place to another. So in this case, to get from this structure to the structure on the left to the structure on the right, we're going to take one of these pairs of electrons, we're going to push it into the single bond to make it a double bond, and then we're going to take one of the pairs that is this double bond and push it on to make a lone pair. So we've gone lone pair to make a bond and bond to make a lone pair. We're always going to go from electrons to deficit and then electrons to deficit. So in turn, we've changed this single bond on the left to a double bond, and then we've changed this double bond on the right to a single bond. And it's always going to show the flow of electrons. There's a couple rules for resonance structures. For instance, if we look at this particular structure, I'll draw it real quick. We have an amine, and then a carbonyl or an aldehyde. We could think about drawing a potential alternate structure where we have, instead of the double bond between the C and the O, we could have the double bond between the C and the N. These would not be considered resonance structures because we've moved arrows completely. So we've gone from, we've changed the connectivity. So we've gone from this H being here to this H being here. So we don't consider these resonance structures because the connectivity is not the same. So the connectivity must be the same to have two equivalent resonance structures. The other big one in organic chemistry is disobeying the octet rule. So let's look at another structure. This is going to be of nitromethane. So we have a nitro group on a CH3. Now you can imagine pushing in a lone pair from here to generate an alternate structure that looks like this. This would formally put another charge on nitrogen. If we look, the nitrogen in this case has 8 electrons in its valence shell. The nitrogen in this case has 10 electrons in its valence shell. We must obey the octet rule unless we're dealing with things like phosphorus or sulfur or things past phosphorus and sulfur that can disobey the octet rule. But in most cases for organic molecules, we must obey the octet rule. So we can't have a situation where we get something like hypervalent nitrogen. Nitrogen does not have access to its d orbital, so it will never go hypervalent. So now let's talk about a concept that goes along well with resonance, which is the concept of formal charge. So formal charge is a way we can track where electrons lie in a molecule. It can influence polarity, it can influence reactivity, it can influence structure, and it's going to tell us a lot about the overall function of a molecule. So for instance, let's look at nitrous acid, HNO2. So nitrous acid has this structure. And formal charge will tell us where, if any, charges lie in this molecule. Now, the formula for formal charge is going to be equal to the number of valence electrons minus the number of bonds minus the number of lone electrons. So let's do that. Let's do an example for one of these. So let's look at this oxygen here. So oxygen has 6 valence electrons, and you can read that by seeing that its valence shell is 2s2, 2p4. So it has 6 valence electrons. It has 1, 2 bonds, so it's going to be minus 2, and it has 2, 4 valence electrons. 6 minus 2 minus 4 equals 0, so the formal charge on this oxygen is 0. If we look at this oxygen up here, we see that its valence is 6. It's got 2 bonds to it from that double bond, and it's got 4 valence electrons, so 6 minus 2 minus 4 is 0, so the formal charge on this oxygen is 0. Now if we look at this oxygen down here, we see that the valence is 6. We're going to have 1 bond to it, so it's minus 1, and then we have 2, 4, 6 lone electrons to it, so 6 minus 1 minus 6 is going to be minus 1. So this oxygen would have a formal charge of minus 1. Finally, if we look at this nitrogen, nitrogen is 2s2, 2p3, so it has 5 valence electrons. It has 1, 2, 3, 4 bonds to it, and it has 0 lone electrons, so 5 minus 4 minus 0 is going to be plus 1. So this nitrogen has a plus charge on it. Now you'll notice that in calculating the overall charge of this molecule, we see we have a plus and a minus, so those should cancel out to 0, and if we look, HNO2 overall has a 0 overall charge. So the formal charges in a molecule will always add up to the overall charge of the particular molecule that we're looking at. Now, formal charge can influence structure as well, or it can inform structure. So for instance, let's look at another isomer of nitromethane. So instead of having the connectivity as we had before, let's do this connectivity. So we have this, 2 lone pairs, and then 2 lone pairs. So let's quickly check the valence charges, or the formal charges in all of these. If we look at this oxygen, we have 6 minus 2 bonds minus 4 lone pairs, which would be 0. If we look at this nitrogen, we have 5 minus 3 bonds minus 2 lone electrons, which is going to be 0. If we look at this oxygen, we have 6 minus 2 bonds minus 4 lone electrons, which is 0. So this is overall, all of the formal charges are 0. Now you can imagine a resonance structure where instead of doing this, I'm going to draw the arrow pushing, we push this in and we push this out. So we could draw a resonance structure where we instead have a structure that looks like this. So it's got a double bond between that O and the N, and a single bond between this O. It's got a lone pair there, and it's got 1 lone pair here. So we could imagine this alternate structure, but let's check the formal charges. So if we look at this oxygen here, we know we have 6 valence electrons, we have 3 bonds, and we have 2 lone electrons. 6 minus 3 minus 2 is going to be plus 1. So this oxygen has a formal charge of plus 1. If we look at this nitrogen, it's going to be 5 minus 3 bonds minus 2 lone electrons is 0. So this is going to have a formal charge of 0. And if we look at this oxygen, it's going to be six valence electrons, minus one bond, minus 6 lone electrons, which would be minus 1. So this would have a minus 1 charge. If we're choosing, so we have two valid resonance structures. However, which one of these would be what we call the most important resonance structure? And the answer would be this one. And why is that? When we're considering multiple different possible structures for a molecule, we want to make sure that we're minimizing the number and the magnitude of the formal charges. So in this case, we have no formal charges that are non-zero. So that's ideal. However, in this case, we have a minus formal charge and we have a plus formal charge. So not only do we have two formal charges as opposed to 0, but they have magnitudes of plus and minus 1. So this would be unfavorable. So we would call this top structure the most contributing or the most important resonance structure. The other consideration to take into account when we're drawing resonance structures is where we place where the formal charge goes. So let's consider the NCO minus ion, which is the isocyanate ion. So we have a couple different possible resonance structures with NCO, and I'll let you confirm those on your own. We have NCO, and then finally we have NCO. Oops, not that many. Just one lone pair there. And finally, 3 lone pairs on nitrogen. So let's look at the formal charges of these nitrogens, carbons, and oxygens to determine which one of these would be the most contributing resonance structure. So again, nitrogen has a valence of 5. There's 3 bonds attached to it, and there's 2 electrons, lone electrons, so this would be a formal charge of 0. Carbon has 4 valence electrons. It has 4 bonds to it and 0 lone electrons, so this would be a 0. And oxygen has 6 valence electrons, 1 bond, and it's got 6 lone electrons, so this would be a minus 1 charge. Note that there must be some kind of minus charge overall because the overall charge of the ion, the polyatomic ion, is minus 1, so this minus 1 will give us that minus 1 overall charge. Let's move on to the next structure. So we have N. It's going to be a valence of 5 minus 2 bonds minus 4. 5 minus 2 minus 4 is going to give us a charge of minus 1. For carbon, we have 4 valence electrons minus 4 bonds minus 0, which will give us a formal charge of 0. And finally, oxygen will have 6 valence electrons minus 2 bonds minus 4 lone electrons, which will give us a formal charge of 0. The final state of this particular polyatomic ion, we could see that nitrogen has a valence of 5. It has 1 bond and it has 6 lone electrons on it. So 5 minus 1 minus 6 is going to be minus 2. Carbon has a valence of 4 minus 4 bonds minus 0 lone electrons gives us 0 as a formal charge. And oxygen finally has a valence of 6 minus 3 bonds minus 2 lone electrons, which will give us a formal charge of plus 1. So which one of these would be the most contributing resonance structure? Let's think about this. Now, first off, we have to minimize the number of formal charges and we have to minimize the magnitude of formal charges. So if we look at this one, we've got 1 minus 1. If we look at this middle one, we've got 1 minus 1. And if we look at this one on the right, we have a minus 2 and a plus 1. So not only does this have a higher magnitude charge, it has a plus 2, but it also has 2 total formal charges. So this would not be the most contributing resonance structure. Now the choice, we have a minus 1 and a minus 1, so we can't compare magnitude or type of formal charge. So we have to choose based on where the formal charge lies. In this case, we have the formal charge lying on nitrogen. And in this case, on the left, we have the formal charge lying on oxygen. Now the formal charge, since it does preclude electron density, we're going to assume and we're going to predict that the minus formal charge will preferentially go on the atom that is more electronegative. If we look at the periodic table and think about our trend in electronegativity, we see that oxygen is more electronegative than nitrogen. So in fact, this structure here with the minus formal charge on oxygen would in fact be the most contributing or the most important resonance structure.